later, they now have past our meeting, past the house. You can come out of Hobbs on the side door, you can get up on the sidewalk and come down right in front of the Arcadia house and out onto Ridgecrest. And then when I get to Ridgecrest, you can go back that way too.
Good evening, everyone. I bet you've never seen somebody juggle 2 laptops at one time, but we're going to try tonight. Before we get started, I have an announcement, and then I'm going to introduce, sadly, the last session of this series, at least for now. So our announcement is the Astronomy Day lecture over at GTCC. I thought I would read the description and give you a few more details about that, okay? So that will be Friday, September 22nd, which, believe it or not, is next Friday, which seems so odd to even think that it's that close. But this will be featuring Dr. Roger Windhorst from Arizona State University, and they will be discussing the recently deployed James Webb Space Telescope that is rapidly expanding our knowledge of the universe, especially at its earliest epochs. This year's Joe Klein Memorial Lecturer Roger Windhorst is Regents and Foundations Professor at Arizona State University and interdisciplinary scientist for James Webb Space Telescope. He and his group at ASU used the Hubble Space Telescope and the JWST to study the formation and evolution of distant galaxies and probe epoch of first light by using gravitational lensing of the earliest stars by foreground galaxies. Please do not ask me any questions about that. If you are curious, we are taking a bus. The bus will be picking up at West again on Friday, September 22nd at, don't want to tell you wrong, at 6:40. So the West bus pickup is at 6:40 p.m. And for Guilford, it will be at 6:50. The lecture starts at 7:30, so we are estimating we'll be back around 9 p.m. So if that sounds like something you're interested in, there are sign-up sheets on the first floor of Woolman at the Activity Hub and over near the Cubbies on the West Campus. Alrighty, so is it walker friendly? Yeah. Yeah, I'm getting a head nod. I've never been to GTCC, so we should go together. But yes, he is saying that it is walker friendly. All right, so our last session tonight that Aaron has been so gracious to come and do for us, and the rest of the series, will be on cosmology and unanswered questions. Can you please give a warm, awesome round of applause for our lecturer tonight?
Thank you. The presentation next Friday is at the it's a big, I forget what it's the big lecture hall right by the lake. But yeah, you can get in, there are walkers, and there's a large auditorium, so you'll be able to manage that without any problem. Yeah. Any other questions about that lecture next Friday night? Oh yeah, the history of the Astronomy Day, when the observatory was dedicated back in 1997, we started with an Astronomy Day, and it's become an annual event that has attracted an amazing array of speakers, including several Nobel Prize people. And people have wondered why they come to Guilford Tech, and the answer is we invited them. So much so that now it's almost a feather in somebody's cap to be invited to Guilford Tech. The reputation has been so strong. In an astronomy day, we invite all the astronomy people from all over the state, and there were a few people initially thought that community college, that was below their level. But when we started getting these speakers, there's no resistance to it anymore. And in fact, we've become probably the ideal location. We're sort of centrally located in the state. And also, who does a community college threaten? Nobody. There are programs that think they are pretty good hot stuff, and they might, there might be some competition, but we compete with nobody. So the programs have been really quite amazing. Okay, well, tonight we look at stuff that even I don't pretend to fully understand, but let me talk about some of it anyway. I think by now you're pretty well convinced that there are a lot of galaxies out there. To quote Carl Sagan, there are billions and billions of galaxies. The actual count of galaxies is really beyond comprehension. And keep in mind that a galaxy may have 100 billion stars. So there's lots of stars out there. Lots and lots and lots and lots of stars out there. If you think it's crowded around here, step out, take your own galaxy, take your own stellar system. There are plenty. And if there's so many stars, what about planets? Are there a lot of planets out there? Well, it was speculated that there probably were, but until recently, a couple decades ago, there was no confirmed evidence one way or the other. But that's changed. In fact, this is a nearby star system, Fomalhaut. You're not going to see Fomalhaut here because it's visible in the southern sky, not in the northern sky. But Fomalhaut is one of the brighter stars in the southern sky. And this is an amazing image. Fomalhaut is a very young star. It's still forming. It's definitely a star, but it's still in the formation process. And probably a lot of dust and gas may still be falling into the star. But take a look at this little box, and here's an enlargement of the box. And look at there. Here's the image from 2004, and there it is from 2006. Something is moving around Fomalhaut. Must be a planet. So there apparently planet formation is probably pretty common. We've wondered about that for a long time, but now the evidence is pretty conclusive that the planets are really probably quite common. So how many are there? Well, as of September 7th, there were 5,514 planets identified. Now, keep in mind, we're not seeing them all. We only look at the ones near close stars, and some of the best detection has happened when a planet moves in front of a star and dims its light slightly. As of September 7th, there were 4,107 planetary systems. That means there were a number of stars that had multiple planets. So it wasn't just a single planet. Which raises, in a lot of people's mind, a very hot question. So is there life elsewhere? Well, I'll pick up on that a little more. There is a very famous called the Drake equation. It's really not an equation, but Drake tried to put together a method to try to figure out whether there might be life elsewhere and how much there might be. So there is the number of stars forming, and then the planets, and then where life could exist, and then where life does exist, and so on. A number of people have been highly impressed by the Drake equation. Frankly, I'm not. Let me give you a multiplication problem. I'd like you to do this in your head, so hang on. 427 times 523 times 6,247 times 0 times 544 times 233. What's the answer? 0. Ah, good for you. You know your math. In a multiplication problem where a series of factors, if any factor is 0, the product is 0. Well, the trouble is, yeah, we know there's a lot of stars forming. We know there's a lot of planets. But you know, I'm somewhat amazed. In all the work of biology, I am intrigued how much we don't understand. Why, with all the effort, has nobody been able to turn on life anywhere? We can synthesize molecules. We can synthesize a lot of the molecules of life, but nobody's been able to kick in the spark that turns it on. And what is that spark? With all the effort, that remains a mystery. So, how much life is out there? Well, I've asked many people how many think there's life elsewhere. And when I ask for a show of hands, the majority tends to think there's got to be a lot of life out there. And people have asked me over and over, do I believe there is life elsewhere? Well, you know what I believe doesn't really matter. The question is, what's the evidence? And the answer is, we don't know. We truly don't know. And when people ask me what I think about life elsewhere, my reply has been, you tell me how you want to be convinced, and I'll convince you. So if you want to be convinced that there is life elsewhere, I'll convince you of it. If you want to be convinced there's not, I'll convince you of it. So we're stuck. And the answer is we don't know. Now, interestingly, there's been a James Webb result that has just been published. There is a planet, K2-18b, whatever that is, where they found an atmosphere, and in the atmosphere they found methane and carbon dioxide. They found some water vapor some places also. I'll get a little more excited if they find oxygen somewhere. Why will I be more excited if oxygen is found? Well, believe it or not, oxygen is a very volatile material. And oxygen doesn't stick around very readily. Yeah, we think there is a lot of oxygen here, but where does the oxygen come from? Free oxygen probably comes from plant life. So if some future observation comes up with the detection of oxygen, that will excite me more than carbon dioxide. Because Mars, Venus, carbon dioxide is quite common. But if there's free oxygen, that would be a significant indicator. And of course, there's the question, if there's life elsewhere and intelligent life elsewhere, why haven't they come to see us? Well, I'm quite sure that the UFOs are not intelligent life from elsewhere. Frankly, if you were coming from outside the solar system, I'm not sure you'd even bother stopping at the pale blue dot. It's not very obvious. And if you did, I can't imagine that you'd stop in some obscure place for a little while and then take off. If you traveled that far, I think you'd probably want to stick around a little bit and see what was going on. So, why haven't they contacted us? Well, anyway. That's a cartoon on our refrigerator.
Read it.
If there are people on other planets, why don't they contact us? And the guy with the telescope simply says, would you? Anyway. Well, the question about life elsewhere is one of the pressing things in certain fields of astronomy. A lot of the push on the satellites throughout the solar system are looking for the possibility of life elsewhere. A lot of the exploration of Mars and a bunch of the moons. One of the curious questions is, might there be life elsewhere? And I don't despair of the search. When the little green man comes along, I'll be delighted to invite him to dinner. And so I have no problem with that, but yeah. I guess my feeling is do good astronomy, discover whatever you can in any area. So I don't totally despair of the search for life. By the way, give me a chance to go to the moon, I'll be packed up and ready to go tomorrow. Give me a chance to go to Mars? No, thank you. There's a lot more complications than people generally realize. So it's going to be quite a challenge. Anyway, so just how big is the universe? We'll try to push that question out. Clearly there's lots and lots of galaxies out there. So that's the fish perspective on the universe. Just a big tank full of water. Another ancient picture was somebody inside the universe looking out through the celestial sphere to see what's outside. Well, can't do that very well. But to understand, I'm going to take a bit of a digression and give you a little bit of physics. I'm not going to get into a lot of mathematics. But to understand the universe, we need to understand the Doppler effect. And believe it or not, you have some experience with that, but let me illustrate. Let's say there's a car blowing its horn. Sound waves will go out as waves from the car, and you will be able to hear it. Now, suppose the car is moving along. In the direction that the car is moving, the sound waves will bunch up, because by the time one wave is emitted, the car has moved, so there's not as much space. But on the opposite side, the waves get longer. So what does sound wave sound like when the waves are shorter and when their waves are longer? Well, you have some experience with this. Did you ever stop at a railroad crossing when the train was going by and it was blowing its whistle? And you hear the ooh, and then when it goes by, ooh. You've just observed the Doppler effect. Or if somebody's going by and blowing the horn, you hear well, I used to like to listen when I was grinding my first telescope mirror. There was the Indianapolis 500. And I'm not that big of a race fan, but grinding a telescope mirror is rather tedious. And so I would listen to it, and you'd hear the racers go by the microphone, you hear the drop in the pitch. Why the drop in the pitch? As it was coming toward the microphone, the waves were bunched up. As it went by, they were expanded. So there's a greater distance. Any questions about the Doppler effect? Does that make sense? Okay, now we're ready, and that applies because light also has wave properties, and so we can look at it from distant star perspective. Now, this should be flipped upside down. Let's start with a local star. Every element has its fingerprints. And if you take the spectrum of a star, you will see, when you pass the light through a narrow slit and then through a prism or a grating, you'll see dark absorption lines very clearly. Now, if this is a local star, and by the way, this is wavelengths in nanometers, very tiny, but anyway, red through violet. If this is the spectrum of a local star, a local galaxy, they're the same lines of the elements, but they're shifted a bit. And then when you get to a distant one, the same lines are shifted further to the right. And a very distant galaxy, they're shifted significantly. you have heard about the red shift. This is the red shift. The spectrum is shifted toward the red. And from that, we can measure the velocity and the movement. Now let's apply this to galaxies. Galaxies are frequently in clusters. And look first at the right-hand column. In the heart of many of the galaxy clusters, there is a very large galaxy. Now, each of these galaxies is probably about the same size. Well, if they're the same size, why are some appear larger than others? Why do you think they would? Closer, that's right. The bigger one is closer. Now that you have that established, this is a closer one, this is much more distant. Let's go to the spectrum. Ignore the comparison line above and below. Look at this fuzzy spectrum in the middle. And that's the only thing I want you to pay attention to, not these lines. Whenever you take a spectrum, you have a source right nearby that gives you some lines that you can measure against. It is not the most common element, but some of the strongest spectral lines are the lines from calcium. Again, not because the calcium is most abundant, it's simply that the calcium produces the absorption lines more readily than others. So, you see those two little lines right there? Those are the lines of calcium. This is the spectrum of the entire galaxy. It's not picking out individual stars. It's just getting the light from the entire galaxy. Now look at the spectrum as we go further away. They're shifted. And there they are again, shifted further, shifted farther, and really shifted. Now again, what produces the red shift? It's moving away. It's almost as if the word has gotten out that the Milky Way is a place to avoid. Practically all the galaxies in the universe are moving away from us. And the further away they are, the faster they're moving. Which raises another interesting question. If they're all moving away from us in every direction, are we at the center? If they're all going away from us? Now, I'd like you to do another thought experiment. Suppose we take a balloon and put ink dots all over the balloon. It's not blown up. And now we start blowing up the balloon. What's going to happen to the dots? They're going to move. Oh, and from which dot will they move away? From all of them. I like to think of a kind of an infinite dough of a loaf of raisin bread rising. And imagine that you're sitting on a raisin and you're looking at the adjacent raisins. No matter where you are, as the dough rises, every other raisin will be moving away from you. It's as if, regardless where you are, you're at the center. So to talk about the center, there may not be a center, or maybe everywhere is the center. "60 years ago, almost 60 years ago, back in 1964, there were two observers, Penzience and Wilson. This was a very special radio telescope. It was designed to pick up very sensitive signals from the Echo satellite. One of the early satellites was just a big balloon that reflected signal, but the signal wouldn't be very strong, so they wanted a very sensitive receiver to pick it up. So they built this very large horn that funneled the radio waves into the instruments inside. This was done at Bell Labs. Tragically, there were a lot of companies used to have laboratory facilities where they simply hired scientists to do good research, whatever they wanted to work on. And Penzience and Wilson were part of the fortunate thing there. Well, they designed their very sensitive receiver, and they discovered that they were getting some background noise. No matter where they pointed it, they had some hiss. Now keep in mind, you're giving off radiation right now. If I had the right camera, we could turn off all the lights and I could still take pictures of you because you're glowing. Maybe you didn't know you glow in the dark, but you do. Now, you're not going to see much in the visible part of the spectrum, but the longer, if I had an infrared camera, I've seen photographs taken where there was a room of people that had left, and you could tell every seat where people had occupied because it was still glowing. And you would glow in the dark, in the infrared. And the longer wavelengths is radio. Now, imagine that we're out in space, nothing interfering, and we set off, I don't care, cherry bomb, stick of dynamite, whatever. So we have an explosion. If we're out in space and there's nothing around, how far will that explosion extend? It'll go on forever. But what will change? What would it look like if you watched it? What would happen to the brilliance of the explosion? What would happen? It gets dimmer. That's exactly right. There were two views of the universe. Edwin Hoyle and a couple of other guys were thinking that there was a steady state to the universe. From the redshift of the galaxies, they knew the galaxies were expanding, but they thought that as the space expanded, new matter filled in, and it just kept going. As it expanded, new matter formed, so that everywhere you looked, it'd be the same forever. That's the steady state universe. Other people suggested, no, that wasn't the case. Other people suggested that the universe had a beginning. And Hoyle thought that was such a stupid idea that he called it the Big Bang. Well, that's the name that it still holds. And when Penzience and Wilson were working with their receiver, no matter where they pointed that receiver, they were always getting a fairly uniform background hiss. It wasn't very strong, but they couldn't figure out what was going on. Now, keep in mind that objects at normal temperature will radiate, and a bunch of pigeons used to come into that radio dish, and they pooped over the dish. And so Penzias and Wilson got in and scraped out all the pigeon poop, thinking that that might be the source of the hiss. But even after they cleaned it up, it was still there, persistent. And they concluded that it is as if the universe must have had a beginning of the Big Bang, and that the explosion, as it expands, is cooling off, and if we go back far enough, it was about as if there was something about 3 degrees above absolute zero. That's around 450 below zero Fahrenheit, minus 273 Celsius. A little on the chilly side. And they suggested that the universe must be glowing with the background radiation of about 3 degrees above absolute zero. So, when you light a candle flame, some of the energy comes in infrared, some of it comes in yellow light, some of it comes in red light, and so on. And so you get a profile of longer and longer wavelengths. And so this solid curve is the curve that would be produced by a black body radiator whose temperature was 2.725 degrees above absolute zero Kelvin. That's basically 2.75 degrees above absolute zero. Kelvin and Celsius have the same scale. The difference is in the Kelvin scale, in the Celsius scale, you start at zero at freezing point. On the Kelvin scale, you start at the lowest temperature that you can get. That is absolute zero. And so here's the curve. And those bars are the measured intervals. They actually measured those. It had to fall between the top and the bottom of each little bar. But look where the center is. That looks like that's a fit. It is an amazing agreement. So what does that suggest? Well, let me take you back to the history, going back to the beginning. Now this graph is a little complicated because the top line is the time in seconds, and the middle line is the temperature, and the bottom line is the energy. But the other thing that is important is the distance scale. If you go from here to here, that's a very tiny fraction of a second. But if you go from here to here, that's 1 billion years to 12-some billion years. So it's not a linear scale. The numbers vary so much that if you put it on a normal graph, it wouldn't make any sense. And so for each interval here, it's a huge jump. So from here you are at 100 seconds, but going from here to here, you're now to 300,000 years. Whereas from here to here, all of this out to about here is all within 1 second of the beginning. So it's stretched so that it will fit together. So what happened? Well, there's the Big Bang. boom. God stepped out and said, boom. Anyway, whatever. And then there's a period that is called inflation. Now, you've heard that nothing can go faster than the speed of light. And that is probably correct. No thing can go faster than the speed of light. But in this early interval, there wasn't even anything. Space itself expanded. And if you can understand that, my hat off to you. But it's not stuff expanding, it's space itself is expanding, and that's called inflation. And Alan Guth came up with that idea. Perhaps the more accurate but harder to understand is this one. Back in the beginning, a period of inflation, very tiny, a point, and then it jumps, and then it continues to expand ever since. And early on, there wasn't even things like atoms. It was too hot for the atoms to exist, particles and so on. If any of you want to go in more detail, I'll be happy to go through it with you, but it gets a little hairy. Another view, again, this is time in seconds. And here you see 10 to the power of negative 40. What that means, 10 to the minus 40, it means put down a decimal point, then 40 zeros and then a 1. That's 10 to the minus 40. As you know, 10 squared, you put down a 1, and then you put 2 zeros after it. 10 squared is 100. 10 cubed, 1 with 3 zeros. So this is basically telling you how many zeros there are. Well, from here to here is all 1 second. And then you go to billions. So it's not, but again, in the beginning, there is very compact with a brief period of inflation, and after inflation, the standard Big Bang theory takes over. In the very beginning, forces were very different. Even gravity probably did not exist. So there's a period of quantum gravity, and if you understand that, good for you. And then there's the inflationary. There are several forces. There's gravity, there's a strong nuclear force, there's a weak nuclear force, there's electromagnetism, and so on. So this is apparently what was going on in the beginning. Quite a soup of particles. Fermi Labs in Chicago is doing all kinds of particles were forming. In the very beginning, up to just maybe about 300,000 years, the universe was dominated by radiation, so much so that we can't see beyond that. But after that, it cooled off enough so that light could get out. Think about it. If you have a hot enough source, light can't even get through it. But if it's cooler, light can get through. So in the beginning, radiation dominated, but then when you got cool enough, matter dominated. So where did the elements come from? This is a periodic chart that I find incredibly fascinating. All the hydrogen in the universe, and you have a lot of hydrogen in your body, probably originated with the Big Bang. So you have part of the Big Bang in you. And most of the helium came from that as well. If you've ever taken lithium medication, some of it came from the Big Bang. Well, if you want to see this further, I can tell you where to get access to this periodic chart. One of the fascinating things is supernova take us pretty well up to, we don't recognize, but you do recognize nickel, copper, zinc, and some of those. Those probably came from supernova, but then some of the heavier elements, if you have gold, it probably came from the collision of some neutron stars. But again, we can go into that more if you would like. So, from the dawn of time, tiny fraction of a second, and then the space expands, and then we can actually find the background radiation, but we discover it's not quite uniform out to the present. The present appears to be around 13.5 billion years since the Big Bang. And the conditions, this vertical line is probably where things emerged, so that for every hydrogen atom, there's quite a few helium atoms, but not about a lot less. And then there's heavy hydrogen and some helium-3 and so on. Well, that gets a little technical. Another view of the same thing. For every, remember that a hydrogen atom is basically a proton, so there's a lot more protons than helium atoms, but then there's some deuterium, and by the way, every cup of water that you drink, deuterium is heavy hydrogen that has one hydrogen and one helium, and that is excellent fuel. If we ever learn to control the hydrogen bomb in a fusion reactor, it will be an incredible source. Somebody said that it would be equivalent to filling the oceans 300 times with fuel oil. That would be a wonderful source of fuel. And the ash, if we control that, the ash is helium. Put it in balloons and let it go. It would float to the top of the atmosphere and float away. Wouldn't be a problem. Wouldn't be a pollution. Anyway, so what's the universe look like now? Well, let me explain this. Some observatories have mapped the location of galaxies, and this redshift becomes a distance measure. So the greater the redshift, the further away they are. Now, why is it blank in these couple areas? Well, keep in mind that from any observatory you can't see the whole sky, so you're limited, and that's the reason. But these are galaxies. Does it look like the galaxies are uniformly distributed? No. It's kind of a spongy texture. Interesting. This is a map of the entire sky. This is the Cosmic Background Explorer. And the difference here is temperature. Red is cooler, blue is hotter. And then a refinement of that. This was the Cosmic Background Explorer, and then a better map of it was this Wilkinson Microwave Anisotropy Probe. But these are temperature differences, which would imply that this stuff would be moving away and therefore a little cooler, and this stuff slightly, the blue would be a little warmer. So there is temperature difference, which indicates that the universe is not uniform. And these spots may represent where galaxy clusters were forming. In more detail, here's a large map. And again, these are galaxy clusters. And it's kind of like a webby appearance. And that's what the universe is like. A bit of a webby background. So what do we think the universe is made of? Well, when you look at all the heavy elements, all the stuff that you know, all the galaxies, all the stars, you and I, everything that we think we know, that probably makes up about 0.03% of the universe. And then there's neutrinos, and they're ghostly little particles that they can fly through you. They can fly through the Earth without hardly touching a thing. Every time you're sitting here, neutrinos are flying through you. And the reason they're flying through you is there's really not that much there. You're mainly empty space. And they can go through without touching anything. Yeah. If you want to tell somebody they're spacey, that's correct. All the stars amount to about 0.5%. So all of this stuff makes up only about 5% of the universe. So what's the rest of it? Well, you may have heard about dark matter. So what's dark matter? Well, if I knew what dark matter was, I wouldn't be standing here. It's dark because we don't know what it is. So how do you know it's there? Well, it shows gravity. There's something that's producing gravity, but we can't see what it is. It's one of the big mysteries. And the dark matter, remember, all the stuff we know makes up about 5% of the universe. The dark matter makes up about 25% of the universe. And more mysterious than the dark matter is dark energy. And what's dark energy? I have discussed this with some of the foremost leaders in the field, and I was told that we have no clue. But there's reasons to believe that it must exist. So do we understand the universe? No. There's a lot to go. A lot to go. To probe it, one of the things is to look for gravity waves, and we're starting to detect them. These are two tunnels, and a beam of light is sent down the tunnel, and it's split into two components. So the one component goes out to this arm to a mirror, the other component goes out this arm to a mirror, and then comes back. But if somebody moves the mirror a little bit, they'll be out of phase with each other when it gets back. Well, something is moving it. There are gravity waves, and these LIGO experiments are now detecting gravity waves. What they'll tell us about the universe, we don't know yet. But if two neutron stars get too close and merge, they actually shake the entire universe. And they can detect the shaking on these experiments. Or if two black holes merge, they can detect the shaking of the entire universe. So we now know that gravity does bend even light itself. In fact, it was in the total eclipse back in the early 1920s, where the theory of relativity was first confirmed because Einstein said that light should be bent. And stars that in a total eclipse are near the sun, Einstein predicted that their position ought to be shifted by a very tiny amount, predicted what it would be, and at that eclipse they measured it, and sure enough it was. So let me explain this. Here's the observer. Here's a very large galaxy. Way back here is a quasar, which is a very, very bright source. But the light from the quasar that goes past the galaxy on this side gets bent a little bit. The light going past the quasar on this side gets bent a little bit. So it looks like you're seeing two of the same thing. And we see those. We actually see those. Here's a very massive galaxy. But wait a minute, these are curved. There's a lot of curved lines. What's going on? Well, the curved lines are probably galaxies in the background that have been bent, and the light is actually amplified. Shows up a little better in this next slide. This and this are probably the same galaxy. So how can you tell? Well, for some objects, if there's a background quasars sometimes flash. And you can see the pattern of flashes in the one exactly matches the other, except it may be off. But it's the same amount of time for each event. And so the gravitational lensing, the bending of the light, is showing that up. So where are we at? Here's the the Webb telescope. Here's a large, massive galaxy. These with the spikes are foreground stars, but there are gravitational lensing. This are probably the same item. So is our picture correct? You know what's happening? The new evidence from the Webb is saying, whoops, some of this is not quite like we thought it was. So maybe we don't know what we're talking about after all. There are two important things in the sciences. One is finding a major new discovery. That's very important. But another important thing in the sciences is coming up against a big dilemma. So why is that important? That gives you a hint on the direction you need to pursue. And some of the work from the James Webb is telling us, there's still some unanswered questions. And that's kind of neat. So in conclusion, that's all I can say. Just keep looking up, keep looking up, keep looking up.
Are we going to get a test?
Would you like one? Yes.
Tell us more about a black hole.
Sure. Do you know what's under the floor here? I assume there's something under the floor. Well, let's go up to the ceiling, to the roof. Suppose we drove a bulldozer or two up in the roof, what do you think would happen? It would collapse. That's right. Now we get down to a solid rock. Can you compress a rock? Actually, you can. If you squeeze it hard enough, you can collapse it. If you take a piece of coal and squeeze it hard enough, at temperature it becomes a diamond. So is there something so rigid that it can't be collapsed? Well, when a star dies, a star like the sun will become a white dwarf. And what will happen? What's holding the sun? Why isn't the sun collapsing now? Two things. Gravity. How big would gravity like the sun to be? Which direction does gravity move? Inward. So if it were strictly gravity, how big would the sun be? How small? Well, gravity would like to take everything down to zero volume. So why isn't the sun that small? Hydrogen fusion is gone. There's energy in there. The energy is pushing it out. Gravity's trying to push it in. Now, when the sun burns out, there won't be more energy pushing it out. So it'll squeeze in, and what stops it? Well, matter is made up of neutrons, protons, electrons, and if gravity gets strong enough, it will squeeze the electrons right into the protons. Actually, before that, it gets so close that the electrons say, we're not going to let you squeeze us anymore. That's called degenerate matter. If the sun became degenerate matter, the sun has how many times the diameter of the Earth? It's less than 100,000, but it's many times the diameter of the Earth. But if the energy quit, the sun would be squeezed down to degenerate matter, and it would become about the size of the Earth. Be very tiny in the sky. But suppose you pile more stuff on top. Well, eventually the electrons say, hey, we can't hold this up. And so there's another collapse. And it goes down to neutrons. And if the sun became a neutron star, it'd be about the size of Greensboro. Now pile more stuff on top of the neutrons. And eventually the neutrons say, hey, we can't handle this anymore. And so it collapses again. But there appears to be nothing to stop the collapse. Well, if nothing stops the collapse, how tiny would it get? It'd go down to zero. We can't comprehend that. But wait a minute. The mass is still there, so the gravity would be very strong, and close to it. Well, somebody I heard say that if you flew over a neutron star and you dropped a marshmallow on it, it would be equivalent to a nuclear blast. I thought that was preposterous. I did the calculation, and sure enough it would be, because the gravitational field is so intense that the acceleration would be so great, the impact would be equivalent to a nuclear blast. But once you get down, if there's nothing to prevent it, then how do you get out? the gravitational field nearby would be so great that not even light can escape. And if light can't escape, nothing can. That's a black hole.
And you said black holes collide.
Suppose you have two large stars, each of which collapses to a black hole. They're in orbit around each other. But in the orbiting process, they lose some energy, so they'll start spiraling in toward each other. And eventually they do collide. And in the process, as they get close, they shake the entire universe.
So that's your gravitational waves.
Yep. It can come from a neutron star, it can come from black holes.
When they show a picture of the black hole and something being swirled, it looks almost like light coming out.
But that's around the outside.
Yes, yes.
That's, and the distance where the speed of light is, where you go the speed of light to go around it, that is called the event horizon. If you're outside, there's a possibility of escape. If you're inside, no. So the event horizon is that boundary. And the images that have been taken of the black hole, the images show dark interior and light around the outside.
When they show or talk about stars being engulfed by the black hole, it's just if the star is close to it, or does it pull it toward it?
Just if the sun became a black hole, we would orbit it just like we do now at our distance. It is when you get inside the event horizon that you're in trouble. But keep in mind, in orbits, you can lose some energy in orbital motion. And if you lose energy, you're going to fall further and further in. Other questions?
I have one other question. Going back to your initial discussion at the beginning of the lecture about is there life anywhere else in the universe?
Right.
Wouldn't there be a point of view that said if there are millions of galaxies and millions of stars within galaxies, and then gradually you're finding more and more planets as your eyes become better as an astronomer, wouldn't the probability be that somewhere there would be other Cinderella planets like the Earth?
There probably are planets similar to the Earth. We know of some that are a similar mass. That we know. What properties do they have? As I pointed out, the Webb telescope has just discovered some atmosphere components. And I'll get pretty excited if I see oxygen in the atmosphere. Hasn't been detected yet. Will it? I don't know. And the big question, biologists have tried like crazy to synthesize life. Why haven't they been able to? What is the trigger? Life appears in all kinds of amazing places on the Earth.
Well, isn't there something called a primordial stew?
Yeah, but does life emerge from it? As I said, you tell me how you want to be convinced and I'll convince you. Yeah. Back in the red hat.
Thank you. How many suns are there?
How many suns are there? By the way, most stars are fainter than the sun. the sun's in the upper percentiles of the stars. So over 90% of the stars in the sky are fainter. But in Milky Way galaxy alone, there are probably somewhere in the order of 200 to 400 billion or maybe a trillion stars. And keep in mind there are billions and billions of galaxies. So how many stars are out there? I'm telling you, there's a lot of stars out there. And we now know that planets appear to be very, very common. So, yeah. Somebody else had a question. Yeah.
Yeah, I'm having difficulty with the concept of a second, way back in the Big Bang, because it seems like, well, seconds move, they vary. And it seemed like it was being described as steady seconds.
Well, yeah, we don't understand what is time anyway.
Yeah.
What is time? It does appear that space is at least 4 dimensions: length, width, height, and the time component. And if you'd like to make sense out of that, I'll explain. I can give you a concept that will help you imagine where time may be a component of space. I won't take time with everybody, but anybody who wants to stick around, I'll go over that with you to help you sort of comprehend how time could be part of space. A second is an interval. What is time?
Especially in first microseconds.
Yeah. In the early universe, fraction of a second, a whole lot happened in the first second. Physics has been able to get back to put down a 1 over 40 zeros. I'm sorry, put down a decimal place over 40 zeros and then you're 1. That fraction of a second, physics has been able to take us back that far. But that last little bit, we're stuck. Now some people are trying, some people have said, well, could there be other universes out there and one universe bumping into another? And there's no evidence for it, but other questions? Yes?
Okay, I'm still back on our sun.
Yes.
And I'm worried, after you've explained how the black hole becomes zero. Now, is there any chance of our sun disintegrating itself into the black hole to know?
No. And the reason is the sun doesn't have enough mass to create a strong enough gravitational field. The evidence is when the energy that's holding the sun out now is gone, all the fuel is used up, the energy, the evidence is that it will shrink down to a white dwarf. And that is what's called degenerate matter, and it would be about the size of the Earth. And that's about 5 billion years in the future. So I'm not highly worried about that. I don't think I'll make it that long. And to tell the honest truth, I don't want to be married to Ruth that long. And I don't want to live that long. Other questions?
telescope found a galaxy so far out that it could create problems with the standard model today? Could you go over that?
The Webb telescope has, it appears that there's a lot of evidence that galaxies form as very small galaxies, and then they collide and get larger. And by the way, we're headed for a collision. The Andromeda galaxy is practically all the galaxies in the universe are rushing away from us. But the Andromeda galaxy is heading toward us. And it looks like in 1 billion years or so, we'll collide. So stick around, watch the fireworks. But the picture was that small galaxies merge to form larger ones and so on. But one of the things that the Webb telescope has shown us is there are far more mature galaxies out there than there should be. So, back to the drawing board. And the number of times it's been back to the drawing board, that happens over and over and over again. We thought the Earth was the center of the universe. And then we said, no, it's not the Earth. The Sun is the center. And then we said, no, it's not the Sun. And so we've had to change our minds a number of times. Any other questions?
Yeah.
Yes.
So do scientists ever consider the fact that dark energy might have something to do with consciousness?
There may be, the question was, do they think that dark energy may have something to do with consciousness? Yes and no. That becomes a philosophic question, not a scientific question. How would you measure something like that?
What if they merge?
I say any other question should be answered after we get this.
Yeah. Thank you. Yeah,
Well, this is just an existential question.
sure.
If human beings such as yourself and others can be as passionately excited about the mysteries of this universe, can we as human beings become as passionately excited about saving this planet?
I hope the question was if we can get so passionate about the universe, can we get equally passionate about saving this planet? And fortunately, the overwhelming majority of the scientific community is very passionate about it. And it becomes, sadly, much more of a political issue than a scientific one. We could do a lot to save the planet now. And frankly, what we're doing, not only have we set ourselves up for trouble, but boy, if the Gulf Stream quits, and we could be close to that. There are a number of things that would make what's going on today look like a picnic. So, yes, most of the scientific community is saying, we better work like mad. Any other questions? Thank you so much for... And if you have other questions, stick around. I'll be happy